Next time you go and lie out in the sun, be sure to use some of this. Because what you'll be doing is lying out in the glow of a nuclear reactor. A distant one, but a nuclear reactor nonetheless. The sun is a star and its centre is fusion heat, millions of degrees, pouring out day after day. And today we're taking two journeys. One is to the centre of the sun. And the second journey is back to 3 minutes after the start of the universe, when the whole of the universe was at the temperature that the sun's centre is today. Now at this point you might say, how on earth can you tell me how hot the sun is? After all, I can't go and put a thermometer in it. Well, come with me and I'll show you. We can look at the sun and we can see it glowing in the sky, and we see the beautiful colours that it gives us. Now colour is a great hint to what's going on. Things that are very hot glow right across the spectrum. The hottest things glow blue, and cooler things glow yellow, and the coolest things glow in the red region. When you say red hot, in fact, you should be saying red cool. It's the coolest of the whole of the rainbow. So just the action of looking at the sun and seeing it with our eyes, the beautiful colour of the sun, tells us the sort of temperature of its outside. Now what we're going to do here in the room is to make ourselves a sun of our own. Bryson over here has got an oven inside which he's going to put a cannonball. Now don't open it up yet, I'm going to tell you what to look for. That cannonball is up over 1,000 degrees, and the moment he opens the front it'll be glowing yellow. Now the moment he brings it out from there, it'll start cooling so fast you'll see it change from yellow to orange to red almost before you can follow it. It'll stay red and gradually cool off, and you'll apparently see nothing at all when it's got cold. But it's not cold yet, it's actually very, very hot. Too hot to handle. But it'll be glowing in the infrared. Now let's do the thing. Look for the orange and yellow the moment it opens. Let's go. So 1,000 degrees, you've got your glowing yellow ball. It's turning to orange already, even as we've got it out into the air. It's glowing down towards the red end now. It's still glowing red as it cools away, and gradually it will cool further and move away from the red and become invisible to the eyes. But as it does that, although our eyes can't see it, it goes away from the visible spectrum. With instruments we can pick it up. This is a thermopile, a special eye that can see beyond the rainbow into the red, into the infrared, measuring heat. If I point this at the bench, nothing's really happening. It's quite cold down here. But if I point it up towards our sun, we see the thing shoot way, way up. It's detecting the heat into the infrared, even though this thing is rapidly disappearing from sight to our regular eyes. So we see here how the colour changes as it cools. Bryson, I think you better get that into the water fast. Thank you. So we've got the idea now that different colours tell us about the temperatures. Red is cooler than yellow, it's cooler than blue. We can go and look at the stars and see for ourselves exactly what they are. We can look at the Orion Nebula, new stars being born. And in the Orion constellation, there's a red star, which is quite cool, and there's a blue star, which is very hot. So we begin to see already the different temperatures of the stars just by looking at them from here. Now the sun is our nearest star, and we can do a lot with that. We can take a spectrum of the light that's coming from the sun. Let's look at that. And here you see the beautiful rainbow right the way across. But in the middle of the rainbow, you see some dark lines. Now this is like a thumbprint, an autograph. It's a spectrum that was showing up the presence of a new element, helium, in the outer regions of the sun. Now all elements give you spectra. You can do them in the laboratory and measure them and start writing down what the spectra look like in a book. It's like fingerprints. So here you've gone and looked at the sun and you found this fingerprint of something. What is it? You go and look in your book like the police do when they're trying to find the fingerprints of the criminals, and you find this fingerprint isn't there. It's a new one. At that moment, people realized they had found the thumbprint of an element that nobody knew of before. And that's how helium was discovered. They called it helium because it was found in the sun. Helios, helium. So here you see how you can look out into space and see what's happening out there. What you have in effect done is gone out to the sun and put a test tube and brought it back home. You can compare the spectrum that you see here from the sun with a spectrum of helium that you could make here in the laboratory. Exactly the same. So what the stars are doing by shining at us and allowing us to look at them is like fax messages. They're telling us that out there in space, nature is doing the very same things that it does here in the laboratory. It's the same everywhere. So we can learn about the stars remotely, all the way across space, like this. But it raises now a very interesting question. If this was 1893, the RI lecturer 100 years ago would have got as far as he could go. Because we're now faced with the problem, how does the sun do it? How does the sun stay burning bright in the sky day after day after day for so long? Well, the first possibility is that it's a chemistry fire, just like the fire in the grate at home. Doesn't work. Lord Kelvin pointed out that if it was just chemistry at work there, 10 million years was the maximum time that the sun could have survived. Far too short for the whole of life on Earth to have developed. So that was the first possibility gone. The second possibility that came to mind then was gravity. Now everybody knows about gravity. We've known about gravity since Galileo and the pendulum. So let's actually demonstrate our confidence in gravity. Here I have another cannonball hanging on the pendulum, and I'm looking for a volunteer who knows all about gravity and trusts me. Would you like to come down? Hi, what's your name?
Julian.
Right, now you're nice and short. Good. Let's walk back over here. Keep walking back until this is over your head. Now, one more step back. Stand very still. Now what we have here is a demonstration of how you can convert one sort of energy into another. This is like being at the top of a waterfall. You've got great potential to turn into energy of motion, as I will reveal now by letting go of the pendulum. You see, it's turned into kinetic energy. It swings quite happily back, and I really believe in the laws of nature that it's safe as long as I don't move, I hope. Thank you. Thank you very much. So that's gravity. We know how it works. We trust it. But then we try to work out whether the sun could be generating energy this way. Could it be that the gases in the sun are collapsing under their own gravity and generating heat? Lord Kelvin did the sum for that as well. And he discovered that even that couldn't last at more than about 20, 30 million years. Now at this point, you have a problem. You've got Darwin's theory of evolution, which was gaining credibility in the late 19th century, and according to that, the Earth was many hundreds of millions of years old. Yet according to these calculations, chemistry and gravity would have only allowed the sun to have lasted for much shorter time. What was going on? One possibility was that Darwin was completely wrong, that the time scales of geology were just completely wrong, and many people thought that was the explanation. The other possibility was that the 1893 lecturer was just short on the script. that there was something else going on beyond the chemistry and gravity that they knew of. Now that is what turned out to be the answer. And we're now going to take you through the century and give you the answer as to how the sun really works. Like detectives, we have to follow with the scientists step by step to see which clues they found and how they put them together. Now the first clue came just after a century ago, 1896, with the discovery of radioactivity. Now radioactivity is the sort of thing where you begin to feel, oh dear, this is all sort of nuclear and bombs and so on and so forth. No, it's not. Radioactivity is completely natural. It's happening all around us now as I speak. In fact, we have developed as animals, we've evolved in a world where radioactivity is happening all the time. I shall demonstrate it to you now. Here are some common or garden objects, almost literally so. Here is a Geiger counter. If I switch it on, you're just listening at the moment to the odd crackle from background around us here. That is a lump of rock that you might pick up in Dartmoor. This is a ship's compass. This is a mantle from a gas lamp. Just remember the rock. We walk on rocks all the time. That's radioactivity. All around us, we have evolved in a radioactive background. That's okay. So you see there common samples of radioactivity. So the scientists in 1896 wanted to know, what was this? What is this strange new emanation? And the people who made the most immediate impact on this were the famous chemists Pierre and Marie Curie. Now what they were doing was on the trace of radioactivity, trying to find out exactly what is it that's giving off this new power. And they started looking around, and they looked in mud and rock and every common or garden thing, and in pitch blende they eventually discovered that something was going on. And chemically, they gradually filtered it down until they isolated the source. And they found some new elements that nobody knew of before. The first they called polonium, after Marie's home country of Poland. The second one was the most powerful radiation known, a new element which they called radium. Now, radium is such a powerful emitter that if you held it in your hand, it would keep you warm. If you turned off the lights, it would glow. If you dropped a single speck onto a photographic film, you could actually see the radiation being emitted from it, shooting out and leaving its traces all over the photographic plate. In fact, early in this century, Pierre Curie gave a talk here in the Royal Institution and unfortunately spilt on the floor some radium. Years later, scientists from Harwell came to the labs here and discovered the spot. It was still pouring out radiation, and they had to dig up the floor to deal with it because it was so harmful. So the Curies had really asked the questions. Radiation is happening, what's going on? And the person who then was the detective who started pursuing this to find the answers to the question was a famous New Zealand called Ernest Rutherford. This is Ernest Rutherford in his more dotage years when he was now Lord Rutherford, Order of Merit, Fellow of the Royal Society, Nobel laureate, unlike when he first came over here when he was a nice young chap like me. He came from New Zealand. It was like the brain drain in those days. Everybody wanted to come and work over here. This is where the action was. And so he went out on the path of radioactivity. He started looking for the various things, and from this he began to discover that radioactivity came in many different forms. Let's repeat what he discovered. I've got here two different samples on the bench top. Let's see if we can hear them. That's certainly working. And that's certainly working. Now, let's see what happened if I put something in the way. So this is clicking away. You can see the dial. Sheet of card cuts the clicks a little bit. On the dial, you'll see it cut quite back. This other source, nothing much happens at all. If I put a sheet of lead between it, then something does cut it off. But the piece of card doesn't do anything at all. To this one, but to that one, it does. So what we've seen here is that there are two different types of emitter. The first, Rutherford being a good classical scholar, called alpha. And the second, he called beta. In fact, there are three, alpha, beta, and gamma. But these are the two that we're going to chase. The alpha particles, we know they're particles because when I put the cardboard in the way, they were stopped. The sound cut off. The alpha emitters are easily trapped. The betas penetrate. Two different forms of radiation. So at this point, Rutherford has shown that radioactivity was actually quite complicated. Wouldn't it be wonderful if we could go and see these particles? And that's what brings us to one of the great discoveries in the early years of this century, the development of the cloud chamber. Now, Bryson Gore has been building this cloud chamber here for several months. It's taken months of his life out. And indeed, this sort of thing here that Bryson has built, the word has already got around, and people are phoning up and asking advice on how to build these things from him. So this in itself is an amazing piece of apparatus that we've got here. Down the bottom here, we've got some coolant, which is keeping this whole evacuated thing at the top here nice and cool, and mists are forming inside it. You can see the mists forming as we look. This originally was invented by a man called Charles Wilson. He used to go hiking in the Scottish Highlands. He really loved the mists, and he tried to reproduce them in the laboratory. He wanted to make atmosphere of his own to study things with, and as a result of that, stumbled on this amazing fact that you will see shooting around little trails. Clouds seem to spontaneously form. The reason here is that in the middle we have got a source of radiation, an alpha particle emitter, an alpha radioactivity. The alpha particles are shooting out, and as they do so, the mist forms on them. You're not actually seeing the particles, you're seeing their footprints. You're seeing where they have been. It's like a plane coming into land and you see the mist forming on the wingtips. Now, this was such an amazing development that Rutherford himself said, at last we've got a telescope that we can look inside the atom and see what's going on. Here, for the first time, you're actually seeing matter breaking down, radiating away, the trails of those alpha particles shooting out into the mist. Now, that is lovely. And I think Bryson's done a remarkable job here producing this for us. I find it amazing as I watch it. It's like eerie, seeing these things happening right before us. Now, what we could also do would be to surround this thing with magnets, because then we would be able to start learning more about these particles. See, if they've got positive charge, the magnets would deflect them one way, and if they were negatively charged, the magnets would deflect them the other way. So by seeing what happens when we put magnets around, we start being able to tell what they're like, how fast they move, and so forth. The second thing would be nice to take photographs of them and then see what they look like and learn about them. Well, let's see what happens when we do that. This is what happens when you take pictures of trails of beta particles. Beta particles, we now know, are just electrons, negatively charged particles, and as they come shooting out into the magnetic field, the magnets turn them. But they keep moving as they turn, so they end up going in this spiral, as you see in this beautiful picture. Now, Rutherford has told us there's more than one type. There's the alphas as well. Let's see what alphas look like. Now, alphas look very different. What this picture here is showing, at the bottom, we've got a source of alpha particles, and the atoms in that source are spontaneously breaking down, and as they do so, shoot out alphas. Any direction. Some shoot out here, another one shoots out on the other side. But what you notice is, it doesn't matter which direction they go, they always seem to reach the same distance. Now, what's going on? Because Rutherford realized that that regularity, the fact they always went the same distance, was important. And it was something that he could put to use. So the first question he had to sort out was, why do they go the same distance? Well, let's think what's happening. An alpha particle shoots out. Now, the alpha particle is much smaller than an atom, a little thing. And it's confronted by this huge crowd, like I am. and it bumps into them and gets slowed down until it comes to a stop. Once it comes to a stop, no more trail. They always get the same distance bumping through the crowd because they always start off with the same speed. That's the key here. This source always ejects alpha particles with the same speed. And at this moment, Rutherford realized he was onto something, because he had got a source of little bullets always coming out with the same speed, which he could use. And the second thing was, he knew that they had positive charge because he'd seen which way they went when you put very powerful magnets on here. And with that, Rutherford decided he could answer the big question of what are atoms made of? Now, why are we caring about atoms at this point? What's special about atoms? After all, we might have thought at the end before that atoms were the last layer in the cosmic onion, peeling deep down into matter. But no. It was already known at the start of the century that negatively charged electrons exist inside atoms. In fact, in every atom of your body, there are negatively charged electrons. And the number of atoms in your body is 1 followed by 27, 28 zeros behind it. And yet, apart from your magnetic personalities, there isn't any sort of leftover magnetism there. There's no leftover electrical charge on you. So there must be some positive charges in you as well, exactly balancing out the negatives to leave nothing overall. And that must be true in each and every atom of your body. So immediately, we know that atoms can't be the end of the road. They've got something inside, negative charges and positive charges. So the big question was, where are they? Where's the positive charges? How are they spread around? How could we know? Well, the idea that came to Rutherford was to use those little alpha particles as a way of answering the question. Let's look at the two possibilities that were around. One was that the positive charges are distributed all over the atom, as in this picture here, the negatives and positives everywhere. If that was the way things were, when you shoot a positive alpha particle at it, it will go just straight through. It hardly meets any resistance at all. Let's suppose the other picture was that the positives were clumped tightly in the centre of the atom. What would happen then? Well, here's what would happen. If you made a direct hit, your alpha would bounce off. In fact, if you really hit it head on, you would be really lucky, it would come straight back. So these are the sort of possibilities that you could use the alpha particles as bullets to distinguish. Are atoms uniformly or concentrated in their positive charge? So that's what we're going to do now, and let's take the second example to see what would happen when you start doing this sort of experiment. So what we've set up here on the table is a sort of topological map of the positive charge concentrated in the centre, and what we're going to do is to fire some positive alpha particles at it and see what happens. Can I have a volunteer to fire some alpha particles around? Would you like to? Hello, what's your name? Aileen. Aileen. Right, Aileen. What I'm just going to ask you to do, in your own time as you like, just put balls in here and fire them at that, and I'll see what happens. That's pretty good. See if you can make a dead hit by moving this, if you like. Okay, put the ball in. Down it comes. Pretty good. You see, it got deflected quite a bit. Try another one. See, getting nearer a very sharp deflection. Let's see what happens next time. 90 degrees, it's gone right off sideways. A little bit more and you might make the dead hit. Fantastic. Thank you very much. So what you're seeing here is what happens when you fire positively charged particles, the alpha particles, those little ball bearings, towards a centre of positive charge at the middle of the atom, if that's what it was like. They would get deflected very violently if they got near in the centre, a bit less violently if they pass on the edge. The second idea of this, of course, is that the alphas are like bullets that you're actually going to fire at things and see what happens. So now what we're going to do is to look at what would happen when you fire the alpha particles as bullets. Can I have a volunteer to do that? Would you come down? What's your name?
Andrew.
Where do you come from?
Manchester.
Amazing. Because everybody thinks that Rutherford did this in Cambridge, and he didn't. All the books tell you he did this in Cambridge, he did it in Manchester. Fantastic. Now, over there is this positive charge. And here is a gun full of positive alpha particles. Now, what I want you to do is to hold this as you feel comfortable, point it at that, see if you can make some strikes, and if you're managing to make some strikes, just spray it around a bit. Let's see what happens when you fire at the atom. Let's go. Say go.
Go.
Thank you. Well, that was pretty good. Who wants to do it again? Would you like to have a go? What's your name? Right, Hannah. Okay. You do the same thing, exactly the same as before. Come over here and hold it how you feel comfortable. Which side do you like to hold it from? This side's best for you, is it? Now, wait a moment. I'm going to take cover. I'm now going to play the role of Rutherford. I'm going to detect the things and see what happens when you fire. Okay, in your own time.
Go.
Fantastic. Thank you very much. I got one. So, if this is exactly what the atom was like, when you get a strong hit, there would be a strong bounce sideways. Whereas if the atom were just the positive charges distributed everywhere, the red ping pong balls would just go shooting straight through. The alpha particle bullets would just go straight through. There'd be nothing really to affect them. So here we've got a way of seeing what atoms really are like. And what my colleagues at the Rutherford Appleton Lab in Oxfordshire have done is to build an exact replica of a genuine alpha particle scattering experiment, such as Rutherford himself might have done, or at least his assistant Geiger might have done. Geiger, the same Geiger, is in the Geiger counter, by the way. This is the first time on television that a real thing like this has been in operation. Let me just show you what's inside it. It's evacuated, so this outer thing here is just to protect me if the thing explodes while I'm talking to you, and you, of course, as well. Now, at the front, we've got the alpha particle gun, and it shoots the alpha particles at this target. It's a wafer-thin target of gold, the very same stuff that Rutherford's team used themselves all those years ago. Now, most of the alpha particles we expect will pass straight through, so we've got a detector out here that will pick them up. But some of them, if the positive charge is indeed concentrated in the centre of the atom, could be detected by a thing out here at a much larger angle. What we can do is vary the position of this one and see what happens as we do so. Now, most of the alpha particles go shooting straight through, and on the dials at the bottom here, we're keeping count. The bottom dial shows you how many alpha particles are being detected out at the front, the ones that just pass straight through without anything happening. And already, nearly 400,000 have been detected in the forward direction, just shooting through. The bell that you hear ringing is each time something is detected by this fellow at the side. It's such a rare event, we've got the bell there to let you know. Now, the point of this is that if the atom had just been a diffuse ball of charge everywhere, nothing would ever bounce back. The fact that any bounce back at all is the key. That was the genius that Rutherford had to realise it was the once in a blue moon that the bell rang that was showing that the positive charge is concentrated in the middle, and occasionally, when by chance the alpha makes the direct hit, when the red ping pong ball hits the football head on, and it bounces back and be detected in this backward direction. Now, we'll leave this thing running. At the moment, the score is 4 in the backward and 536,000 in the forward. But it's the 4 in the backward that are the crucial ones. And occasionally the bell will ring, and when it does, you will know that here in the theatre, an alpha particle has been scattered by the nucleus in the centre of an atom. You are seeing it proved, or hearing it proved, right here and now. Great. These sort of things happen totally by chance. I was terrified that I would speak for 20 minutes, nothing would happen, and then like number 11 buses, 3 rings would go when I didn't want them. But there you see it, or hear it. So as a result of this, we've established, or Rutherford and his team have established, that the atom has got its positively charged concentrated right in the middle. And that picture has survived right through to the present day. And this is what it looks like. Bipin, can you show us this beautiful model of the atom that you've made and give it a twirl? Should we bring the lights down so we can get the full glory of this thing in the theatre? There's the positive charge, the nucleus, red in the middle, and the negatively charged electrons whirling around on the outside. Should we give it a twirl? There you get a feeling for it. And that picture of the atom, the nuclear atom, has survived 80 years. That is what we now know to be the case. Discovered all that time ago. Thank you, Bipin, for that beautiful model. Of course, the question I haven't told you is, but how small is that charge in the middle? And that is where Rutherford's real genius came into play. By the rarity of the ice cream bell going off compared to the frequency of the thing shooting straight through, you may already have had a feeling that the positive charge can't be very big. But Rutherford, by a very simple calculation, showed how small it really is. What we've got here from the Cambridge University Library are the 2 crucial pages from Rutherford's notebooks where he first realized how small the nucleus in his atom really is. His writing isn't the neatest thing in the world, but we forgive him a few things. In here is the one time in the whole of this story I'm going to show you an equation. Another alpha particle strikes just on cue. What he was interested in here were the rare occasions when the alpha particles bounced right back. They came shooting in and were turned around in their tracks. Why do they stop and get turned around? They come shooting in, they're being repelled, sent back where they came from, and for a moment they come to a halt. Because at that moment, the speed, the energy they started with has been exactly balanced by the force pushing them away. And this is what his equation says. On the right-hand side is the amount of force pushing them away. On the left-hand side is the energy his bullet started with, the half mv squared. And he's going to weigh those two against each other at the moment they come to a stop. And so he takes this up this side and that at that side and that down there. The higher mathematics is all done. He knows everything on the right-hand side, and he's going to put the numbers in and work out what this distance is. How close in does that little alpha particle get before it's turned around? Because that's going to be a measure of how big that nucleus actually is. So you turn the pages of the book. On the next page, you see this is genuine when he makes mistakes and crosses them out. Not like you or me who erase it and try to get our alpha plus for neat and tidy work. Down here, you see something which the younger members of the audience might not recognize. This is long division. And he makes another mistake, but that's not the important thing. Here is the crucial thing. That distance, the measure of the size of the positive charge that we now call the nucleus, is a millionth of a centimetre. Now, at that moment, Rutherford realizes that he's onto something. And his excitement, you can almost see it because his writing becomes almost totally illegible. In fact, it's only recently I've found out what the second word here is. Let's see if you can read it before I can. since something, radius of atom is of the order of 100 millionths of a centimetre, to be compared with the millionth of a centimetre. It is seen that the distance of approach of the charge centre is very small compared with the radius of the atom. That is the point. Rutherford has discovered that the relative size of his positive charge is minute compared to the size of the atom. Now, this is really amazing for several reasons, one of which is that at that time, at the beginning of the century, when Rutherford is doing this experiment, or at least Geiger and Mars and his assistants are doing it, but Rutherford, being the clever guy, got the credit, this works marvellously, just when I need it. What he has done is shown, first of all, even that atoms exist. That second word is probably. Since probably the radius of the atom is. He was even aware they didn't understand everything, and the uncertainty was there. He has shown that atoms really exist, and also that the positive charge is trapped in that little bit in the middle. And that's why he got so excited. And it's from that we now have our picture of the atom, which has survived to the present day. Can I give you an idea for the feeling of the relative size of that positive charge in the middle and the whole thing? Well, let's scale it up. Here, for golf fans with their suntan cream, is a long fairway in a golf course. You will hit the ball here. After several shots, you'll get about here. If you're like me, after several more shots, you will land in the water. And eventually, you'll get it over to where you're trying to reach. That little flag may be 400 meters away. Now, the size of the ball that you're trying to get into that little hole, relative to the length of the whole of that fairway, is like the size of the nucleus compared with the radius of the atom. In all three dimensions, you begin to get a feeling that this is remarkably small, this nucleus in the middle, the positive charge. That's one way of demonstrating it. Anybody here support Peterborough United? Am I the only one? Well, this is close to my heart. I begin to feel that we supporters are as rare as those backscattered alpha particles. If I put this football in the middle of Peterborough, this would be like the nucleus in the atom. If you live in a city of 100,000 people, this football, compared to your city, is like the nucleus in that atom. Well, we can't bring the cities here. We're a bit short of supporters. But we can bring the atom here to the theatre. Let's suppose that the atom were as big as the theatre. I've brought you a measure of the nucleus in here as well. Can somebody with good eyesight come and help me find this? Nobody with good eyesight. Have you got nice? Great. Hello, what's your name?
Alex.
Right, Alex. Now, hanging from the ceiling here, somewhere in the theatre, we've got the atomic nucleus. For those people at the back who can't see it, can you find it?
Yeah, just there.
The ball bearing here. Right. Can everybody see the ball bearing? Does everybody agree that that's the atomic nucleus? No. The ball bearing actually is just holding this wire in place. The nucleus is that little knot in the wire that we have added. Thanks very much. Now you really know how small it is. So, we've established that the atom is not the last layer of the cosmic onion. The atom is made of the positive charge in the middle and the negative charges whirling around on the outside. The atomic nucleus has been discovered. Now, scientists don't like hanging about. The moment they discover the nucleus, they want to know what's going on there. What's the nucleus made of? Is that the last layer of the cosmic onion, or is there more inside? Well, to help answer that question and to show how it was done, we're going to play a game of nuclear billiards. And to help us with this, we've got Teresa, who is a champion, but I should probably say a snooker champion, but I shall call it nuclear billiards, I'm sorry. Okay. Now, what I'm going to ask Teresa to do, I'm going to be pretty tough on her. I'm not wanting her to show her regular skills. What I want you to do is to very accurately just hit this ball without any trick effects. And what I'm going to ask the audience to do is not to watch where any individual ball goes, But watch the two balls as they go apart from each other and look at the angle between them. It should be something like a right angle. Okay. Okay. I wish I could do that. Right. For those of you who are blinking or falling asleep, let's try one more time. Okay, you've got that? Well, no expense spared here. We've videoed that in slow motion. Let's see what happened. So this is the slow motion picture of what Teresa has just done. Watch the cue ball coming in. When it hits the red, the 90 degrees. That's what happens when something of the same mass strike each other and recoil. So, going backwards and forwards, there you are, the 90 degrees. So that's the signal that two balls of the same mass have hit each other. Now what Teresa's going to do is, first of all, show us what happens when you hit something that's much lighter. The angle between them is much narrower. And finally, when you hit something that's much heavier, it bounces back, a very wide angle between them. Thanks very much. So we've seen there on the billiard table what happens. You can bounce things of different masses against each other, and from the angle between them, work out the relative masses. The same mass at 90 degrees, lighter particles narrow, heavier ones big. And we can now do that in our cloud chamber with real nuclear particles. So the first picture shows what happens when we fire nuclear particles of the same mass against each other. They leave trails which move out at 90 degrees, the signal of equal mass bouncing. The next picture shows us what happens when you hit something that's lighter than the cue ball. In this case, a nuclear cue ball has hit a lighter nucleus, and the angle between them is less than 90 degrees. And the final picture, when you hit something that's heavier than you, the thing bounces back. The angle is much bigger than 90 degrees. So just from this, you're seeing that you can start measuring the relative weights of different nuclear particles just by looking at the angle of bounce. The cloud chamber is being used to demonstrate the real world of the atomic nucleus. It's the very same rules of momentum and bounce that apply on the big billiard table are applying here in the world of the atomic nucleus. It's being brought to life. You're seeing the trails of where the nuclear particles have been. And this is really what particle physics is all about. We look at hundreds and thousands of pictures like these and gradually be able to decipher them and work out what has been going on. In this particular case, we've worked out the relative masses of the nuclei of different elements. And at the end of all this, the message is finally deciphered. That all elements, the nuclei at the center of their atoms, are made of essentially the same stuff. Two basic particles, the proton, which is positively charged, and its twin, the neutral neutron. Protons and neutrons put together build you up the atomic nuclei of all the various elements. In fact, everything, solids, liquids and gases, deep at the heart of the atom, the nucleus, is always made of those same two things. The simplest of all, hydrogen, has just got a single proton at the heart of its nucleus, whereas the next one, helium, has got two protons and two neutrons. And so it is right the way across the whole of the atomic elements. And finally, it's this fact that is going to give us the answer to what's going on inside the sun. The fact that all the different elements are at the nuclear level made of the same basic ingredients, the protons and neutrons, means that we can break the nuclei apart, change one element into another. Transmutation of the elements, what the alchemists have been trying to do for years, has finally been achieved. Rutherford, when he realized this fact, realised the incredible thing that had been done. You could make gold. Unfortunately, it took more effort and expense to make gold this way than to dig it out of the ground, but the idea is there. So you can change one element into another by changing the way that the basic protons and neutrons in the nucleus hang together. So finally from this, we've come to the key of how the sun works. It all hangs on these two, the lightest of all. Hydrogen with its single proton and helium with its 4. It was around 1920 or so when Arthur Eddington got the idea and put it all together. Suppose that the sun is made of hydrogen. Nobody actually knew that for sure, by the way, at that stage, but hydrogen we now know is the most common stuff in the whole of the universe, and the sun and all stars are essentially hydrogen. If these little protons of the hydrogen bumped into each other, they could fuse together and build up heavier nuclei, like this of helium. That was his idea. Maybe the fuel was hydrogen and the waste product helium. That was the first part of it. The second thing, though, which really got him excited, was very accurate measurements of the relative masses of these nuclei, such as we've been doing in the cloud chamber bouncers, showed that the total mass of these 4, when bound together in helium nucleus, was a little bit less than 4 individual ones of the hydrogens that started it off. Now that was a surprise. And he thought, you start off with 4 lots of mass, you bind them together, and a little bit has disappeared. Mass has disappeared. Albert Einstein, E equals mc squared. Mass can be turned into energy. That little bit of mass that's disappeared has been turned into energy, the energy of the sun. Now, it may only be a little bit of mass, but look, it's multiplied by a number here, which is the velocity of light, which is a large number. In fact, it's a large number squared, so it's a huge number. So Eddington then realised that little bit of mass that had disappeared when you started with 4 protons and brought them together to make the single nucleus of helium, that was being emitted as energy, and that is where the power of the sun was coming from. Terrific, but there's a problem here. And the problem is that each of these little protons has got positive charge. And one of the things that we always learn is that like charges repel. You try bringing positive charges together, and they don't want to come together and fuse and build up the heavier elements. They just want to stay apart from each other. How on earth are we going to do that? Well, let's first of all see if we can do it here. We have got 2 protons on the front of the bench. Can somebody come along and help me bring them together? Who would like to have a go? Right. What's your name?
Dorothy.
Right, Dorothy. Now, if you hold that at arm's length, just at the tip there, and this other one also at arm's length at the tip here, and just try gently to bring them together. It's not easy, is it? Right. Now, you probably think that she's cheating. Let's. Right, thank you. Anybody else give a try? Nobody wants to. Do you want to have a try? Right. You hold, again, that very gently at one end. Show proton to everybody. Right. An upside down proton. Let's try an upside up proton, and whatever this one is saying, like that. Righty-co? Right, point them towards the camera. Very gently see if you can get them together. No, they just don't want to go. It's very difficult. Thanks very much. So that shows you how difficult it is to get 2 similar things together. What you're trying to do in the sun is to get the 2 protons together at a distance less than a millionth of a centimetre. That's going to be incredibly difficult. How on earth is it possible to do it? Well, the extra ingredient that the sun has got is heat. The centre of the sun is incredibly hot. In this particular case, it means that the things are moving around very violently. And as a result of that, they can crash into each other. If I threw those two protons together violently, they would crash, even though they want to stay apart. And once they've crashed together, they can fuse and build up the nuclei of helium and generate energy. So that's how the sun burns. And in fact, not just the sun, but any star. From this insight, one can now understand how stars work. Stars start off as hydrogen gas in space. And gradually, gravity does pull it together. It starts under its own weight, falling inwards. And as the hydrogen falls in, it starts bumping and friction warms it up. A star is born. It starts eventually glowing infrared. You can't yet see it. It then enters the visible spectrum, just like the cannonball in reverse, and then glows white and all the way around its cycle until eventually all the fuel is spent, all the hydrogen has been used up. This is the life cycle of our sun. Eventually, all the hydrogen will have gone and the sun will end its life. And in our particular case, it will grow into what's called a red giant. Now, don't worry about this too much. I mean, when the sun's burnt out, that's it, no tomorrow. But thankfully, it's at least 5 billion years away. The sun was born about 5 billion years ago, and it's now in middle age, about halfway through its life cycle, with 5 billion still left, so you can sleep easily tonight. I gave a lecture like this a few years ago, and at the end of it, somebody said to me, did you say 5 billion years left or 5 million years? And I said, 5 billion. And they said, oh, that's all right then. Of course, different stars have different endings, but they all have the same sort of beginnings. The way that they end up just depends upon how much hydrogen there was to begin with. If you've got more hydrogen than the sun or less hydrogen than our sun has, your end of the life might be as a black hole, or it might be that you manage to take on a new life where the helium waste products themselves start fusing and building up the nuclei of even heavier elements like carbon and oxygen, the stuff that we're all made of. And such stars do exist, and they sometimes explode. We call them supernovae, and they throw all of that carbon, oxygen, iron, and all the heavy elements out and pollute the universe with them. And such a star exploded just as our own galaxy was beginning, the solar system here. And that's how the carbon and oxygen in this room originally got here, by stars exploding. So we now know how the stars work. It's all fusion going on inside. Looking out at the stars, you see what nature can do out there. It gives you ideas to what you might be able to do down here, things that you might never have thought of before. Wouldn't it be wonderful if we could reproduce that fusion power of the sun here on Earth? Because the fuel for fusion is hydrogen, and hydrogen comes from water, and water is everywhere. So we'd have a wonderful fuel source. If only we could reproduce that incredible temperature, like the centre of the sun, tens of millions of degrees, we could then bring those protons together and build up waste products and produce energy. So the first thing you have to do is to produce the 10 million degrees. And we have got some colleagues in Manchester who have brought us this powerful machine here. It says off. It is off, is it? It is. Thank you. You will see why I took care of that in a minute. So we are going to build up electric charge on here and then release it in a pulse. It will send a brief current around the metal wire, and these magnets will then transfer that inside the tube to a gas which is sitting inside this tube here. This donut is called a torus. And in that moment, it will heat the gas to a temperature of 10 million degrees. One of the things you have to do to create fusion power. So I will now retire from this and hide behind the bench while Bryson powers up our small prototype of a fusion reactor. Just keep watching the donut and wait for the flash if it works. There you see it. That gas, when it exploded in that thing for that moment, was at a temperature of about 10 million degrees, the same sort of temperature that you see in the centre of the sun. Now, that is 1/3 of what we have to do. In order to make fusion work and be practical as a power source, you need to do three things. You need to get the temperature high enough, and you're seeing that before you. You need to have the gas dense enough. Well, this gas is very rarefied. And you also have to get the spark going long enough. But as you see here, the spark only flashes for a brief moment. But this is 1/3 of what they're trying to do in the fusion program to produce fusion energy. And I think for safety, we better let Bryson turn that off before, in my excitement, I touch it and turn into a real bright spark. Thank you, Bryson. My nerves feel better immediately. So we have shown you here a temperature of 10 million degrees, the temperature that exists in the center of the sun, the temperature that the whole universe was at only 3 minutes after the start of time. And now at last we can begin to put the pieces together. We have seen the center of the sun, we know how it works. Nature has given us this possibility and given us ideas of what we might do here to replicate it. But we begin to understand how the early moments of the universe must have been. 300,000 years after the Big Bang, the universe finally was cold enough that atoms could stay together. That the simplest atoms, hydrogen, with the proton in the middle and the electrons on the outside, could remain together and progress through the universe. Before that time, the universe was much hotter, so hot that the atom couldn't survive like this. The individual pieces, which we now know are electrons and protons, would be whirling around completely independently of each other, making what we call a plasma. What you saw just now was a plasma. The sun is a plasma. The electrically charged particles, electrons and protons, moving around independently of each other. That's what the universe was like before 300,000 years. Right back to the first 3 minutes. It was at that time when the protons themselves were being formed. And we're going to go back even earlier than that. We're going to go back to the first second and see what the universe was like when the bits and pieces that made up the protons themselves were being formed. And that's for next time. Thank you.